Today we're going to start our class number 25. So we're going to talk about transient heat conduction, but we are going to I mean, what is going to happen like when the solids are having finite conduction and convective resistance at the same time, and Biot number vary between 0 to 100. So last class we actually solved LAMP thermal analysis, LAMP parameter thermal analysis, where Biot number was less than 0.5. If you remember correctly, but actually Biot number varies when there is a finite conduction happen in a semi-infinite solids, and as well as there is a convective resistance. So we're going to consider these cases now. So let us first examine. So here you can see I have given here. So we are going to consider transient heat conduction in solids with finite conduction and convective resistance. So it is happening at the same time. Simultaneously, there is a conduction as well as convection happening. So as you can see here, this is a finite plate or finite solids which are having a length of 2L, right? So if it is a center is at the center, the mid plane, if it is the center line, then here actually extended L and this side you extended L in the X direction. So having a thickness of 2L, right? And then we are consider heating and cooling of this plane wall. And this has been extended in the infinitely it is being extended in the Y and Z direction. As you can see, this is X direction, this is having a thickness of 2L, but in Y and Z direction, that is out of the plane or out of the plane of the paper. And one is the vertical distance. Actually, it has been extended infinitely. So let us assume this wall initially at an uniform temperature Ti. Okay, this is given initial temperature is given Ti, as you can see. And then both the surface, that is X plus minus L, this is minus L, this is plus L, or actually that's 2L, are suddenly exposed to and suddenly exposed and maintained at an ambient temperature which is given by Ta. So what happens? This is initially at a temperature Ti, and then the surface, the thickness, this edges are being exposed to an ambient temperature of Ta. So the differential equation is going to be this is just the Fourier's law, d square T by dx2 equal to 1 by alpha dt by d tau. Here actually small t is actually temperature difference and d tau is the time difference, that is actually thermal gradient, and alpha is here thermal diffusivity, if you remember correctly, right? So this is the boundary condition is given at tau 0, that is at time 0, T is actually Ti. That is true. At tau 0, T equal to Ti, that is initial temperature, and then at x0 means at the center line, right? There is no thermal gradient or temperature gradient, right? So dt by dx is 0. But at x plus minus L, that is at the edges, right? At the edges, what is happening? I said that there is a finite conduction and convection. So as you can see, at x plus minus L, Ka dt by dx, that is the finite heat loss due to conduction is equal to Ha T minus Ta. That is the heat loss due to the convection. So one is heat loss, another is heat gain, right? So as you can see, this is actually equal. So what is this signifies? That thermal conductions or finite conduction is equal to the convective resistance, right? Because Ka dt by dx is equal to Ha T minus Ta. This is actually the formula or the expression for convective heat transfer loss, and this is the expression for conductive heat transfer loss. So these two are equal, right? So conduction heat transfer equal to the convective heat transfer at the wall surface. And if you solve this equation with this proper boundary condition, after rigorous mathematical analysis, you get T minus Ta, Ti minus Ta is equal to f x function, that is f is a function of x by L, HL by K, alpha tau by L square. HL by K is actually here what Biot number, if you remember correctly. Alpha tau by L square is actually Fourier's number, and x by L is a dimensionless number, right? So what it actually says that this T minus this is when the conduction resistance is non-negligible, a function which indicates that the location of point within the plate where temperature is to be measured or recorded. And if it is actually you are considering it's a plane wall, if it has been sphere or cylinders or any other thing, then x by L is represented by r by r, right? Where r is the radius, capital R is the radius, r is the distance, right? Now, how do you solve this expression? The most important thing, you get this expression, that is the temperature difference is a function of Biot number, Fourier number, and dimensions number. So you cannot mathematically solve this. So actually what happens? people actually plotted it in a chart format that is known as Heisler chart. So actually, I'm going to show it in the next slide. So it's been graphically represented, and that is known. See, it is known as Heisler chart, which depicts the dimensionless number T0 minus TA, Ti minus TA. Now, as you can see here, T0 comes. T0 is actually temperature at a midpoint. Okay, that is the temperature at a midpoint, right? And it is been plotted with 1 over Bismuth, 1 over Bi, that is the 1 over Biot number, right? For solid or different geometrical shape, either for plate or spheres or cylinder, right? These charts provide the temperature history of the solid at its midpoint, that is x plus minus x equal to 0. Temperature of the other location are then worked out by multiplying the midpoint temperature by a correction factor. As you can see, T minus TA, that is T minus TA, Ti minus TA, that is actually given by theta by theta, which is actually nothing but you can write this form T0 minus TA by Ti minus TA, that is this Heisler chart times T minus TA, T0 minus TA. So this is actually you can determine from the Heisler chart and then you solve for the T, right? The value of Biot number, Fourier number used in the Heisler chart and evaluated from a based on the characteristic parameter S, which is the semi-thickness in case of plate, or in case of or the radius, half of the radius, or radius, sorry, in case of cylinder and sphere. So I'll show you the how does the Heisler chart looks like. This is a Heisler chart. As you can see, the y-axis is T0 minus TA, Ti minus TA, and the x-axis is Fourier's numbers, right? So this is different Fourier number 1, 2, 3, 4, all this. And as you can see, these lines actually represent Biot number, right? So this is for different Biot number. So if you calculate Biot number, right? If you know the Biot number, then you can easily calculate this parameter, right? You can just extrapolate this line, and then for a particular Fourier number, you can extrapolate. So you have to know Biot number and Fourier number, then accordingly you can determine this number, right? So this is so easy. This is, then as you can see, this is for the cylinder, right? Similarly, Biot number and Fourier number, this is all different Biot number, this is Fourier number. So actually, these are actually Heisler chart. So this chart has been used to determine the various parameters. This is another Fourier chart, a Heisler chart. Now this is another expression. They are actually, instead of Fourier number, here Biot number is given. So T0 minus TA, Ti minus TA with the Biot number given, and then x by L is given. X by L is the dimensionless number. So if you know x by L, then again you can calculate Biot number, and then from Biot number you can calculate Fourier number, right? So this is different expression. This is for plate and this is for cylinder, and this is for sphere. So this is little different, but the parameter, this is R by R0, because in the sphere it won't be x by L, it will be R by R0. Similarly, I think for cylinder also R by R0 given, right? Only for plate is x by L is given. So this is actually different parameter. So I'll show you how does this numerically solve. I'll show you a couple of numericals, so it become easy for you. Let us look into this numerical, solve numerical. So it become easy for you to understand. A 60 millimeter thick large steel plate. Thermal conductivity is given 42.6 watt per meter C. Thermal diffusivity alpha given 0.043 meter square per hour. Initially at 40 C, is suddenly exposed on both sides to an environment with convective heat transfer coefficient 25 Kelvin per meter square C, and temperature of 50 C. Determine the center line temperature and temperature inside the plate 15 millimeter from the mid plane after 4.3 minutes. Okay, so these are the two things you have to determine. One is the center line temperature, another the temperature inside the plate 15 millimeter from the mid plane after 4.3 minutes. All the parameters given, 12 given 60 millimeter, that is 0.06 meter, thermal conductivity given, alpha given, initial temperature Ti is given at 440 C, and thermal conductivity is H is given, right? And ambient temperature given, T time is given 4.3 minutes. So first thing first, we have to determine the characteristic length, that is LC, that is for plate it is thickness by 2, you all know, right? So 0.03 meter. Fourier number, you know, alpha tau by LC square. You determine this. Biot number, you determine this, right? So as you can see, Biot number is less than 0.1. As I mentioned, Biot number should be less than 100, greater than 0.1 at the start of this presentation. The internal temperature gradient are not too much, therefore internal resistance cannot be neglected. Thus, the plate cannot be considered a lump system, because lump system is always less than 0.05, right? If you remember, or less than 0.1, right? Further, as the Biot number is greater than 1, Heisler chart can be used to find the solution problem 1. we are going to use the Heisler chart. The first thing is that how do you identify which things, which parameters or which equation needs to be used? You first calculate Biot number and then verify it, whether Biot number less than 0.1 or greater than 0.1. If it is less than 0.1, then you have to use the lump parameter thermal analysis that which we have solved in the last class, right? And if it is greater than 0.1, like in this case, you have to use the Heisler chart. Now, you can ask, how do you know Heisler chart? Because Heisler chart will be provided. If I give you any problem in the exam also, definitely I'll provide you the Heisler chart so that you can easily calculate. So from the Heisler chart, Fourier number is given 3.424 and 1 over Biot number actually 6.06. So these two parameters can be used for plate, and then x by L0 midplane. You can, from Heisler chart, you can see this is 0.6. 0 minus TA, Ti minus TA, 0.6 from Heisler chart. That's why I have, I circled this. So this is you are getting from Heisler chart, because this is the parameters given midplane. So you are getting from Heisler chart. Now substitute this value because all the ambient temperature, initial temperature, you know. So if you put this, then the midplane temperature is coming to 84 degrees centigrade, right? Because T0 is the midplane temperature. Now temperature inside the plate, 15 millimeter from the midplane. So distance will be 15 millimeter from the midplane. X by L, so it will be 15 by 30, 0.5. Because X is the distance being penetrated, right? L is given, so it will be 0.5. Again, X by L, you know, Biot number, you know, 6.06. Again, 4.11. That is this last one, right? We get this T minus TA, Ti minus T, 0.9. So, and again, you solve for it, and then you get it 276.98. So as you can see, there are two parts. One is the midplane temperature. This is you get T0, and then X by L, you know, and then you solve for temperature at the 15 minute after 4.3 minutes, right? So you calculate for this, right? You calculate for T 276.98 degrees C. Another, for example, we'll look into it. A 6 mm thick stainless steel plate, density given 7800 kg per meter cube, specific heat given 460 joule per kg C, thermal conductivity given, is used to form the nose section of a missile. It is held initially at an uniform temperature of 5 degrees C. Then the missile enters the denser layer of the atmosphere at a very high velocity. The effective pressure of the air surrounding the nose region attains the value of, effective temperature of air surrounding the nose region attains the value of 2150 C. The surface convective heat transfer coefficient estimated at 3395 watt per meter square C. If the maximum metal temperature is not to exceed 20 C, determine maximum permissible time in this surrounding and inside surface temperature under this condition. So see all the parameters given. Stainless steel plate thickness given, 12 given 6 mm, right? Density, specific heat, thermal conductivity, initial temperature, ambient temperature, and midplane temperature at 1100 C is also given. So first characteristic length you determine, then Biot number you calculate, HL by K. H is given, right? H is 3395, it is given, right? Here convective convective heat transfer coefficient 3395. L you know, K you know, K is thermal conductivity given 55 watt per meter C. So this part the Biot number 0.185, again Biot number greater than 0.1, right? So therefore lump analysis cannot be applied in this case. Further, Biot number less than 100, hence the Heisler chart has to be used. Now corresponding to 1 over Biot number, that is 5.4, and X by L1, right? Outside surface of nose section, we can get from figure 4.11, T minus TA, T0 minus TA, 0.93. Now you can write this T minus TA, T0 minus TA, T0 minus TA like Ti minus TL in this form. Right. Ti minus TA will be this. Now T0 minus TA, Ti minus TA, and this is already you have given 0.93. So you solve for this 0.495. Now again from 4.8 corresponding to the dimensionless number, 1 over Biot number is 5.4, we get Fourier number 4.4, that is alpha tau by LC square. Now alpha tau by LC square again written by, alpha can be written K by rho Cp, right? Tau LC square, K you know, rho Cp you know, so you can determine tau, that is the time, 2.58 seconds. Okay, so actually from Fourier number it determines the time. Inside surface temperature, again you can use this expression. This is 0.495, we have already calculated, right? So you inside surface temperature, ambient temperature, you know, initial temperature, you know, solve for it. It is coming 1100. 1100.06 C. So actually different part you have to use, and then from high structure you get the value and solve. Okay, as simple as this. So let us look into another last example. A 120 millimeter diameter apple, density given 990 kg per meter cube, specific heat given 4170 joule per kg, thermal conductivity given 0.58 watt per meter C. Approximately spherical in shape, is taken from a 25 degrees environment and placed in a refrigerator where temperature is 6 degrees C. An average convective heat transfer coefficient over the apple surface is 12.8 watt per meter square C. Determine the temperature at the center of the apple after a period of 2 hours. So first R, we have diameter is given, so we have to radius is 60 millimeter, density, specific heat, thermal conductivity, initial temperature, ambient temperature, convective heat transfer coefficient, tau, all these things given. So characteristic length for a spherical is R by C, but actually it is 4 pi R by 3, you get 0.02 meter. Biot number HLC by K, you get 0.411. So again, Biot number greater than 0.1, but less than 100, so high structure need to be used. 1 over for Biot number 2.267, Fourier number, you can get 0.238, right? R by R 0, that is mid plane. So again 4.13, T0 minus TA, Ti minus TA 0.75. You solve for T0, 20.25. As simple as that, because it has to calculate the mid plane temperature. So it's very simple. Only thing is that you have to use this chart from the high stress number for define R by R 0, and then 1 over Biot number this, and for Fourier number 0.2328. Okay, as simple as that. Now let us look into another aspect. If Biot number is towards infinity, okay, transient heat conduction in semi-infinite solid, this is little bit different, but again we are going to look into it. So a solid which extends itself infinitely in all direction of space. So if it's been infinite in all direction, it is known as infinite solid. Now if it's been infinite solid, is split in the middle by a plane, and each half is known as semi-infinite solids. Okay, because one side will be finite, but the other side will be infinite. So that's why it is known as semi-infinite solid. In a semi-infinite body, at any instant of time, there is always a point where the effect of heating and cooling at one of its boundaries is not felt at all, because one side is the mid-plane. Effect the mid-plane. The transient temperature change in a plane infinitely thick wall is similar to that of a semi-infinite body until enough time has passed for the surface temperature effect. So let us look into this figure 4.14. Consider a semi-infinite solids. As you can see, this is the semi-infinite plane. This side is finite distance. This is semi-infinite plane. Initial temperature is given by Ti, and it's been bounded by a surface x equal to 0. This is x equal to 0, and extended in the infinite directions in the positive x direction. The entire body is infinitely at an uniform temperature Ti, that is initial temperature Ti, including the surface, that is this surface. The surface temperature at x0 is suddenly raised to Ta. That is x0 is suddenly raised to Ta, that is ambient temperature for all times greater than tau 0. So what does that mean? That the moment the time is exceeded 0, I mean there's little bit excess of time, the surface temperature at this x0 has been attained Ta instead of Ti, right? So the governing equation remains same, but the boundary condition will be different here. Why? Because initially the temperature x0 equal to Ti, right? But the moment that temperature becomes 0 to tau, the tau is greater than 0, is become Ta. This is the second boundary condition. And the third boundary condition is at the infinite distance and tau, again it is Ti, but for tau greater than 0, right? So at the x equal to 0, it is Ta, but actually x infinity, tau, it is Ti. So these two you have try to understand. This is function, this is 0 mean at x0, and this is time. So this is distance, this is time, and this is temperature. So at distance 0, temperature is Ta, but tau greater than 0. But again, distance infinity, tau greater than 0, but tau it is infinite in Ti, right? So at this surface become Ta, not the whole surface. Okay. Now if you solve for this differential equation with the boundary condition for temperature distribution, you get a complex equation which is known as error function. So that is actually Tx tau minus Ta, Ti minus Ta, error function of Z. Right? That Z is given by x by 2 square root of alpha tau. Here alpha is the thermal diffusivity. So this is known as error function. So this is a Gaussian error function which is actually This error function is known as Gaussian error function. Is Gaussian error. You can see this is being plotted, and there is a table. The error function z is given by 2 by square root of pi 0 to z e minus eta square d eta. This is the function. Error function at 0 equal to 0 and for infinity is equal to 1, right? So at when x this error function 0, the value is 0, and when error function infinity is 1, and in between there is a different variant between 0 to 1. The parameter actually the value varies. The table 4.1, I'll come to that. This is table 4.1. This is, as you can see, this is the error function, and for different z value you get different error function value. And at z 0 actually error function is 0, and infinity it is 1. But other value at the z value you can see different error function value you get. So this error function table or the error function table need to be used to get the value. So let us look into this, how to solve it. We got the error function now by inserting in the definition. This is the equation, right? So you can rearrange this term and then you get t x tau ta minus plus ti minus ta to square root of pi 0 to the e minus eta square d eta. If you differentiate this equation, you get del t by del x ti minus ta square root of pi alpha tau e to the power minus x square by 4 alpha tau. The instantaneous heat flow, it is that at any given x location, because only x is the varying here, within the semi-infinite body is given by qi minus ka ti minus ta e to the power minus x square by 4 alpha t by square root of pi alpha t. Now by substituting this value of del t by del x in the equation, and the heat flow at rate at the surface, that is at x equal to 0, is given q surface minus k ti minus t square root of pi alpha tau. This is the equation, right? Total heat flow is given by this formula minus 1.13 k ti minus t square root of tau by alpha. The general criteria for infinite solution to apply to a body of finite thickness, the criteria is that L by 2 by square root of alpha greater than equal to. Now for cylinder and sphere, instead of x we have to substitute by radius r. So this expression become t minus ta ti minus ta error function alpha tau by r square. For the cylinder and spherical sphere, the error function alpha tau by r square, as you can see, can be obtained from figure 4.6. For different alpha tau by r square value, you can extrapolate and get the error function value. Right? There is another parameter called penetration depth and penetration time. Penetration depth refers to the location of a point where 1% of the change in the surface temperature. So 1% it will be t minus ta, ti minus t will be 0.9. Now this corresponds to x by 2 square root of alpha tau 1.8 from the table of Gaussian error integral. The depth d, which the temperature perturbation at the surface has penetrated, is given by this formula. And penetration time is the time tau p taken for a surface perturbation to be felt at the depth in the range of 1%, that is given by d by square root of alpha tau p 1.8, and then tau p you calculate. So you have to just remember this expression. Tau p d square by 13 alpha, and the depth d equal to 3.6 square root of alpha tau. You don't even need to remember. If it has been asked, I will definitely provide you the expressions. But again, just refer this solution because this is a complex derivation. I don't want students to remember this or memorize this. But again, you should know what is error function is, and when error function need to be used. It actually only need to be used when Biot number is to the power infinity, and for a semi-infinite solid, you have to use it. So let us look into a couple of numericals, solve numericals, so that it becomes easy for you to understand. Now let us look. It is proposed to bury water. It is proposed to bury water pipes underground in a wet soil, which is initially at a 5.4 degrees C. The temperature of the surface of soil suddenly drops to -6 C and remains at this value for 9.5 hours. Determine the minimum depth at which the pipe be laid if the surrounding soil temperature is to remain above 0 C without water getting frozen. Assume the soil as semi-infinite solids. For wet soil, take alpha, that is thermal diffusivity 2.75 into 10 to the power -3 meters square by alpha. So initially, Ti given, initial temperature 5.4, ambient temperature is given -6 C. And you have to calculate, determine the minimum depth at which the pipe be laid when remains above 0 C. So T should be 0 C, alpha given. The minimum depth was just 0, the temperature at critical depth will just reach 0 degrees C after 9.5 hours. With the expression you have to use the error function. T minus T8, Ti minus T8, error function x by 2 by square root of alpha tau. T is 0. T alpha already have known minus 6. Ti 5.4, T alpha minus 6. So it becomes 0.526, which is actually equal to error function x by 2 square root of alpha. Now, you know, you have to determine x, alpha, you know. Time also given 9.5 hours. So here you see alpha tau, you didn't use the change the tau 9 second because alpha was given in hours. So actually alpha and tau, that's why it's hour get cancelled. You solve for it, and then you will get x equal to 0.162 meter. Okay, so that's simple as that. Let us look into another point, another solved numerical. The initial uniform temperature of a thick concentric wall, concrete wall, alpha given 1.6 into 10 minus 3 meters square per second. Of a jet engine test cell is 25 degrees C. The surface temperature of the wall suddenly rises to 340 C when the combination of exhaust gases from the turbojet and spray of cooling water occurs. Determine the temperature at a point 80 mm from the surface after 8 hours. Instantaneous heat flow rate at the specific plane and at the surface itself at the instant mentioned as R1. Now use the solution for semi-infinite solution. But first thing first, you have to first verify the Biot number. You haven't done that here. But please check the Biot number. If it is infinity, then only you solve it or use this error function. But anyway, initial temperature given 25 C, ambient temperature 340 C, alpha given, thermal conductivity K given 0.94 watt per meter C. Tau given 8 hours, X given 80 mm, right? Thickness of the plate. The temperature at a point 0.08 meter from the surface, T minus Ti, Ti minus T, error function this. So T is Ta, error function this, you just multiply. Now error function is, you know the value, right? X no alpha T, you calculate 0.37. So T will be Ti initial temperature, ambient temperature 340, 0.37. Ti initially 25 minus, so you can solve for it to 23.45 degrees. That is the first case, the temperature at the point 80 mm from the surface after 8 hours. The instantaneous heat flow rate at the Pacific plane, you can, I have already show you the expression instantaneous. This is the expression Qi minus Ka Ti minus Ta error from x to the exponential minus x square by 4 alpha tau by square root of pi alpha t, pi alpha tau. So similar expression is used instantaneous heat flow rate. All the parameter you know. Then you solve for it, you get minus 1303.08 watt per meter square of wall area. The negative sign shows the heat loss from the wall. The heat flow rate at the surface itself, again the surface temperature, again it has been shown K Ti minus Ta square root of pi alpha t, you solve for it, and it's become minus 1476.6 watt per meter square of wall area. Okay, I hope you understand this. So these are the two numerical I have given. You solve for it, and then next class, that is next Wednesday, first class or second class, probably first class, we're going to review all this numerical which has been given today or even tomorrow. Okay, all right, thank you.